Hello and welcome back. Today we will look at another example of conservation of momentum. The specific example we're working with today is a child running with a known speed and jumping onto a stationary skateboard, and we will see how we can use the conservation of momentum to determine the velocity of the child on the skateboard after he is on it. So here's the specific problem we want to solve today. Jake, whose mass is 20 kilograms, runs to the right at a speed of 5 meters per second and jumps onto a stationary skateboard with a mass of 4 kilograms. And we want to determine the speed of Jake on the skateboard after he's on it. So as discussed before, we will use physics recipes or solution steps that are common for certain types of problems. And for conservation of momentum problems, here are the solution steps. Our first step is to identify a system of objects with no net external force acting on it, because that's when momentum is conserved. In this case, we know that Jake applies a force on the skateboard as he jumps on it, and the skateboard, according to Newton's third law, applies a force back on Jake. But if we define our system as the skateboard plus Jake, or Jake plus the skateboard, then there is no net external force acting on our system. And so we can use conservation of momentum. The next step is to sketch the before and after situations of the system. So the event here is Jake jumping onto the skateboard. So the before image would be Jake running toward the skateboard. So here's Jake running toward a stationary skateboard, which is placed here. And I'm going to note some of the specifics. We've got mass of Jake is 20 kilograms. We got mass of the skateboard is 4 kilograms. And we have Jake running to the right with a speed or velocity of 5 meters per second. So that captures all of the information for my before image. My after image looks like this. We now have Jake on the skateboard, and the two are moving to the right, and we want to determine the final velocity of both of these. So let me mark this as the initial Jake. And the final velocity is for the combined object of Jake plus the skateboard. And so here's our after situation. So we got the first step done. We've got the second step done. The third is to establish a coordinate system. In our case, with everything happening in the horizontal direction, the best is to define our x-axis in the standard way as increasing to the right, and y-axis increasing to the top, even though once again we don't need the y-axis in this case. So there's our third step, and we have listed a lot of the known information already here, and we have identified our unknown here. So step 4 is kind of captured in our diagrams. So now let's see how we solve for this. The law we're going to use in this case is conservation of momentum, which simply states that the change in momentum of the system equals 0 when there is no external force acting on it. And another way to write that is that the initial momentum of the system equals the final momentum of the system when there is no change in it. And as we discussed in the previous video, the momentum of the system is simply the vector sum of the momenta of the individual objects in the system. So our initial momentum of the system would be mass of Jake times the initial velocity of Jake plus mass of the skateboard times the initial velocity of the skateboard. And here are our vectors in this case. And so now I can plug in the values. So I've got 20 kilograms for mass of Jake times plus 5.0 meters per second. The plus takes care of the velocity part, or the direction part of the velocity. And then the mass of the skateboard is 4 kilograms, but it's not moving initially, so the initial speed or velocity of the skateboard is 0. So this will simply be 0, which will give me 100 kilogram meters per second. The final momentum of the system would be the mass of Jake times the final velocity of Jake, which I'm simply going to write as Vf, because Jake and the skateboard both share the same final velocity, so we don't have two unknowns here, it's just one. So we'll just call it Vf. And then for the skateboard, we got mass of the skateboard times its final velocity, which is also Vf. And now again, putting in the values, I've got 20 times Vf plus 4 times Vf, which gives me 24 times Vf. And as a final step, all I got to do is set the initial momentum of the system equal to the final momentum of the system, which gives me 100 equals 24 times Vf. And to solve for Vf, I divide both sides by 24, which gives me Vf is 4.17 or 4.2 meters per second, rounding to two significant digits of our inputs. So there we have it. That's our fifth step, and we've got a speed for the combined object of Jake on the skateboard as 4.2 meters per second. To the right, so putting in a plus here again shows us the fact that we are specifying the direction explicitly, and that answer makes sense. We would expect Jake to slow down a little bit after jumping on the skateboard because there is more mass moving now. So hopefully you can appreciate now that the momentum conservation is a powerful way of solving problems which have a pretty complex profile of forces of interaction between objects, which we can ignore. We don't have to worry about those, and we can simply look at a system that's got a no net external force acting on it, and then use conservation of momentum to solve for motion dynamics like we just did. So that concludes this slice of physics where we looked at an example of using conservation of momentum to solve for details of motion after an interaction between objects. Thank you.